label the data. Finally, we will incorporate some learning techniques to generate more diverse, subtle expressions for this simple robot system. And in this workshop, we are open to suggestions on the robot learning. Thank you.
Okay. We're moving quickly here, but please keep your questions, write them down, and talk to the authors during the poster session.
The second talk is on improving inference of human intent by modeling language feedback.
Today, I will be presenting my work on improving inference of human intent by modeling language feedback. This project is co-advised by Konidaris and Stefanie Tellex. So the problem that we are trying to solve is that how can we enable a conversational robot to monitor humans' progress as they perform multiple hierarchical tasks?
You can't see the video?
No.
It's still stuck on the old window.
Oh, okay. So just share the screen instead. Probably that's the issue.
Hello, everyone. My name is Ifrah Idrees, and today I will be presenting my work on improving inference of human intent by modeling language feedback. This project is co-advised by Konidaris and Stefanie Tellex. So the problem that we are trying to solve is that how can we enable a conversational robot to monitor humans' progress as they perform multiple hierarchical tasks? And how can they do that by incorporating not only just the observations about the world sensor and human actions, but also by incorporating language feedback from the user in response to the question asked by the robot. Now, a lot of work has been done on plan recognition, but there is no one work that enables modeling of humans' progress in a hierarchical concurrent task setting while handling both partial observability in world sensors and the language. So what we envision is our dialogue manager that builds context and awareness of the environment and of the human's activity by using an hierarchical task network to maintain belief over the human's progress in the task and a sequential, partially observable Markov decision-making representation that allows it to plan based on the dialogue intents and the belief over humans' progress and world state, generate a language policy. We evaluate the performance of our HTN Dial PalmDP planner over various cooking tasks such as making tea, making coffee, and washing hands in a simulated environment presented by Wang et al. In 2017. We show that by incorporating language feedback along with the world state information, our planner is able to improve accuracy of goal and step recognition in completing the task. One sample graph is shown on the right-hand side where you can see that the goal and step recognition accuracy of HTN Dial PalmDP is way greater than HTN, and this is constant even when the sensor reliability is decreasing over time. I will be more than happy to answer any follow-up questions that you have and present even more result in the poster session. So see you there, and thank you so much for listening to my presentation.
Okay.
Thanks. Our third talk would be a natural and efficient interactive learning framework for human-robot social greeting.
Yes,
okay, I'll share the screen. Can you see the screen now?
Yes.
Yes.
Okay. So my name is Mohan from Rijke University Amsterdam, and today I'm going to share my work on natural and efficient interactive learning framework for human-robot social greeting. So as we all know that embedded social interaction requires appropriate timing of initiation and response between different social agents. Although we as human, it's very simple to do that. It remains a challenge for the robot to learn such social skills. So we propose such a learning framework to solve the learning problem specifically for the social interactive task settings. More specific, our work, we are more focused on social and use it as a benchmark task. We hope that our framework can help the robot learn the social skills more efficiently, and also the human teacher can teach the robot these skills in a more natural way. Specifically, our framework is going to use the hierarchical structure, which is divided into the multi-level and the behavior level. So for the motor level, we are going to use imitation learning and let the robot to learn the motor skills for different social behaviors, such as bump face, high five, handshake, etc. And after the robot learns the social skills, it will then use the interactive learning for the behavior level. So for every time step, the human teacher might give some feedback to the robot, including both the suggestive feedback or evaluative feedback. And the robot, with the help of the teacher, might hopefully narrow down the search space and more efficiently understand when to choose the correct behavior for their work, including some functional tasks and latency tasks for real human interacting with the real robot in real time. We proposed a evaluation matrix regarding the learning efficiency and also the teaching experience. So for the learning efficiency, we are going to evaluate in terms of the training time and also the feedback workload. And for the teaching experience, we're going to design a questionnaire and let the human user to score their teaching experience in terms of naturality, the flexibility, the naturalness, and also the satisfaction with the whole system. And there remain some limitations in our work. So for example, like the data requirement for the motor level might be huge. We are going to use more advanced IR algorithm to improve the data efficiency and also combine with some online data updating to solve the problem. And also for now, we don't really have the policy refinement for the motor level. So for the next step, we are also trying to utilize the human feedback for both the motor level and the behavior level. And finally, we hope that our framework can be generalized to different human users. So in the future, we are also considering to introduce some and learn latent variables to further infer the hidden characteristics of different human social behaviors and integrate it into the state design and help the robot to be more adaptive to different human users. Yeah, so that's it. Thank you.
Thank you. Our next talk would be pedagogical demonstration and pragmatic learning in artificial tutor-learner interactions.
I'm Hugo Caselles-Dupré and I'm presenting pedagogical demonstration and pragmatic learning in artificial tutor-learner interactions. In our paper, we draw inspiration from the fact that human demonstration involves pedagogy, with showing rather than doing a task, or disambiguating between different goals. Also, human learning involves pragmatism, with interpreting what the tutor communicates and deducing relevant information. In our paper, we make the following contribution. We adapt pedagogical tutors and pragmatic learners to AI learning setups, and we provide an analysis of the benefit of adopting such approaches. We use the draw two balls environment, which is adapted from Guszti and al., and purposely introduces goal ambiguity. In the environment, the agent has to pick two balls consecutively, and given that choice, it can reach different goals. There are two phases where we create the naive tutors and the pedagogical tutors. The tutor is trained to master all goals using policy improvement, and it rewards itself and updates its policy when trained to reach goals. The pedagogical tutor is the same as the naive tutor, but introduces a Bayesian mechanism to predict the pursued goals for its trajectories. We then create the naive learner and the pragmatic learner. The naive learner is trained using demonstration from the tutor and attempts at predicting the associated goal and rewards itself for correct prediction. The pragmatic learner is the same as the naive learner but adopts a mechanism for detecting strong sampling and deduces information about actions that are not relevant for any particular goal. Here you can see the naive and pedagogical tutor policies, and with pedagogical demonstration there are no ambiguity regarding the pursued goal. This clearly shows in our predictability results, where we can see that learners that are trained with pedagogical demonstration can better predict the associated goal to demonstration. Finally, we have our reachability results, and we can see that learners that are trained with pedagogical demonstration and with pragmatism can learn faster than other types of agents. Thank you for your attention, and you can see the paper on arXiv. See you at the workshop.
Thank you. Our next presentation is called MELD, Personalized Meta Learning for Robotic-Centric Imitation Learning.
Maria, I'm sharing, or do you want to share your screen?
Yeah, if you don't mind, since I have some animations that I'll be stepping through.
Sure. Sure.
Thanks. All right. Hi, everyone. My name is Mariah Schrum, and I will be presenting on our work, MELD, Personalized Meta Learning for Robot-Centric Imitation Learning, co-authored by Erin Headland-Body, Nina Morman, and Matthew Gombolet. For robots to operate in the real world, they must be able to learn novel tasks from end users. They can do so via learning from demonstration. Prior work has shown that robots learn well via robot-centric learning from demonstration, in which the demonstrator provides corrective feedback to the robot. However, prior work has also shown that humans tend to be suboptimal and heterogeneous when providing this corrective feedback. To solve this problem, we introduce what we call mutual information-driven meta-learning from demonstration, or MELD. MELD meta-learns a personalized embedding describing the way in which an individual is suboptimal, and then utilizes this embedding to learn a mapping from suboptimal labels to better labels. We demonstrate our MELD architecture in a driving simulator domain. In this domain, the robot rolls out its current policy and the human provides corrective feedback that may be suboptimal. Based upon this corrective feedback, we then learn a personalized embedding describing the way in which the individual is suboptimal. MELD then utilizes this personalized embedding to map suboptimal labels to better labels. We demonstrate our MELD architecture in a human subject study in a driving simulator domain. In this domain, the goal is for the demonstrator to teach the car to drive from a start location to an orange ball with no collision. We compare our MELD architecture to baseline algorithms, dataset aggregation, and behavioral cloning in a within subject study. In this study, we demonstrate that MELD achieves a lower average distance from the goal compared to prior work. Additionally, we show that MELD achieves a higher probability of reaching the goal once, twice, 3 times, and 4 times throughout the study. Lastly, we demonstrate that MELD is rated better in terms of workload, likability, perceived intelligence, and trust. We'd like to thank our sponsors, and we'd be happy to take any questions at the poster session.
Thank you. Our next talk is on adaptive imitation learning for multi-agent games.
Hey, can you guys hear me?
Yep.
Hi, everyone. I'm Andy, and actually we changed our title last minute. It's called Conditional Imitation Learning for Multi-Agent Games. So the goal of our work is to learn AI agents that can collaborate with different users. For example, how musicians can collaborate with each other. So not just one partner, but potentially many different partners from some partner distribution. So there have been prior work that focus on this setting, but usually they assume access to the environment, or you can query the different partners, but that might be difficult. For example, how can we have different pianists in our living room that we can just train against in an RL setting? So instead, in this work, we look at the imitation learning setting, where we have to learn to coordinate, but we can only sort of watch videos of experts doing so. So a standard multi-agent imitation learning framework doesn't really work because they only output joint actions, doesn't let us adapt to new partners. So in our work, we try to model and infer sort of the latent space of the partner strategy so that we can condition on this latent space and output a conditional policy. So one problem with this is that a lot of these imitation learning data sets are scarce for these coordination games. For example, we might only have 8 training trajectories for each layout in this cooking game we looked at. So the key insight, and we can't query the environment for more data. So the key insight in our work is to look at a low rank prior, because it's been suggested in literature that sort of the Q function of the RL setting can be low rank, or that your human partners can also exhibit low rank behavior. So using this insight, we ran a user trial, user study on 50 users playing this cooking game through their web browser. And we showed that using our method, we were able to sort of adapt to the user's strategy and improve our performance after adaptation. So in summary, learning to collaborate with new partners is difficult in domains with only offline data. And we introduce a new framework to handle adaptation. And these data sets are often scarce, so we propose using a low rank prior to learn from only a few samples.
Thank you. And our final talk is APRAL, a library for active preference-based reward learning algorithms.
Yeah, hello everyone. I'm Eiben from Stanford, and I'm going to talk about an open source Python library, April, that we recently released. This library provides us useful tools for active preference-based reward learning. So let me start with a problem definition. Let's say we have a user who wants a robot to perform a task, and the user has an internal reward function that he wants the robot to optimize, but the robot doesn't know this reward function. To mathematically formulate it, let me use this example. The robot is tasked with reaching the notebook on the table while avoiding the obstacle. The psi here shows an example trajectory. We assume there is a known function phi that maps each trajectory to a set of features, such as the average speed of the robot. And the robot gets a reward that's some function of these features parameterized by W. The goal in reward learning is to learn this W. This is a very common problem, and preference-based approach, which I will explain in a bit, provide effective solutions. But unfortunately, there is no unified library or benchmark for preference-based reward learning. Everyone builds their own code base for the specific project they're working on, and this is not great for reproducibility or efficiency of comparing different approaches. So we decided to develop a unifying Python library that we call April. First, April allows users to give passive data to the robot, such as demonstrations. The only requirement is a human model, which is a model of how likely each data sample is. With this model, April builds a belief distribution over the reward parameters W, and it then refines this distribution by querying the user with some questions. This is the idea in active preference-based reward learning. One example query is pairwise comparisons. The robot shows two trajectories to the user, and then we ask the user whether they prefer trajectory A or trajectory B. Again, all we need is a response model for the human. For example, we can use the softmax model here. But the designers are not restricted to the query types that we implemented. They can come up with new types. And after the robot queries the users with a question, the user responds to the query. And note that the robot here can decide what query it wants to ask the user. Therefore, it can optimize the query using some acquisition function and possibly the dynamics of the task. And any task that follows the environment structure of OpenAI Gym can be used in April. And April allows us to try various acquisition functions for active learning and batch selection methods for batch active learning. At the end, we assess the quality of the learned W or the posterior distribution. If you're interested in using April in your projects or just want to see examples of how it's used, you can use this link or scan this QR code to reach more resources. Thank you.
Thank you.